Hey everyone, welcome back. We're going to look at our second lesson in reciprocal functions and how to graph them. But this time we're going to deal with some of those quadratic reciprocals. Last time we dealt with linear functions and their reciprocals and what that looked like. But now we've got to deal with some of the more complicated ones, those quadratic functions. So when we're going to go graph quadratic reciprocals, this is very similar to graphing linear reciprocals, okay? Vertical asymptotes occur when the value of that function is equal to 0. Okay, that's your x-intercept, because when I go to divide that, essentially to flip it, I'm going to take 1 divided by that value that makes it 0. That gives us a problem, so I can't really do that. And the invariant points occur when my value of my function is either positive or negative 1, and we looked at that last time. So if that's a little fuzzy, you can always check back into the previous video and take a watch through that really quick. It's important only to translate the characteristics of a quadratic function to reciprocal functions, okay? So I've got a function here. It's defined by f of x is equal to x minus 2. So this would be a linear one. So we're going to go through this example first to remind us of all that stuff we did last time, and then we'll take it a step further and look at the quadratic. So we're asked to find the equation of its reciprocal function 1 over f of x. So really what I'm going to do is take that original function, that f of x, and we're going to say the reciprocal now is 1 over x minus 2. So all I've done is taken that original function and put it into our reciprocal. Okay, we're asked to do a couple things. We're asked to sketch the graph of the original x minus 2, then use that graph to sketch the reciprocal on the same grid, and then we'll check it with our calculator here. So we've got to know a couple things. We need to know if there are any asymptotes. So our original function, f of x is equal to x minus 2, would give us an asymptote if this value was equal to 0, like it says above. So if that's the case, I want to locate where x minus 2 is equal to 0. So that means if x is equal to 2, this would give us our vertical asymptote. So I'm just going to use VA for short. Okay, so there's a vertical asymptote. We talked about last time how we could have horizontal asymptotes as well. Now, since our degree on the top part of our fraction is smaller than our degree on the bottom, essentially the top part has a degree of 0. That's a constant. On the bottom, my degree is 1. So my horizontal asymptote then is going to be our x-axis, right where y is equal to 0. Okay, so we're going to go just mark those out on our grid, give us an idea of where we are. So we said as long as x is 2, that would be my asymptote, and along with my axis. So here it gives me some boundaries where I can't cross. So that's going to help us when we go to draw this. Now, if we can locate some points that don't change when I go to flip my function over, that's going to help us even more. So I need some invariant points. Okay, so we'll do those in a different color, kind of break it up. So invariant points. Now, I could have invariant points where my original function is equal to 1, or that original function is equal to -1. Because if I take the reciprocal of 1, that means I'm doing 1 over 1. That doesn't change. Okay, so that's going to be the same. And if I do that to -1, take the reciprocal, divide it by 1, so essentially flip that fraction over, I still get -1, okay? Now, as a fraction, that 1 is 1 over 1. So when you flip it, you get the same thing, which is what I'm trying to show you here. So let's go find out what x has to be to get those invariant points. Now, on one hand, x could be 3, or x could be equal to, and my brain doesn't like thinking sometimes, so we'll just use our calculator and add to both sides. Because the negatives are so important here, it's not a bad idea to always double check. So I could have 2 potential x's. So one of my points is going to be 3, 1. The other one is 1, -1. So I can go graph those on here. So 3, 1 is roughly here, and 1, -1 down here. So you can see I've got 2 points now on opposite sides of those asymptotes. And now I should really have a good idea of what this graph is going to look like. So remember what an asymptote is. I actually can't cross it because there's no value that exists there. So I'm bounded by the 2 asymptotes that we've drawn. So now I know that my graph of my reciprocal function roughly has this shape. Now remember, I'm going to get infinitely close to those asymptotes, but never actually cross them. So there's what this looks like. Now, remember what our original function was, because we are asked to graph them on the same grid. My original function was x minus 2. That function is linear. Okay, so f of x equals x minus 2. That's linear. It's got a slope of 1. There's no number in front of that x. It's got a y-intercept of -2. So I can plot my y-intercept. Now my slope, since it's 1, that means I have a rise and a run, which is 1/1. So we're going to go up 1 from that purple point, right 1 to get our next point, which is going to be one of our invariants. Now if I keep going, up 1 over 1, up 1 over 1, you'll see we hit our other invariant point. So now what I'm actually able to do is connect those dots using as straight a line as I can get, because this is now what my original f of x looks like. And you can see it does cross through those invariant points like we said, and there you go. So now you've got the purple, which was our original f of x, the blue, which is our reciprocal, on the same grid. And we can go graph this very quickly just to make sure that we have in fact done it correctly. So there's x minus 2. We're actually going to go bold that line. So if I move all the way left, it'll highlight this little line here, and if you press enter, you get a couple different designs. So we're going to actually pick the one that gives us a bold. So it should be the second option in your calculator. Leave the other line alone so we can actually see them differently. And we'll do 1 over, and remember the brackets because we had that issue last time, x minus 2. If I hit graph, there's my line, and there's my reciprocal function. And again, we talked about what that weird that line is. That's essentially the asymptote. The calculator just draws it in there when technically it shouldn't actually be there. Just remember that those two pieces for our reciprocal should be separate. So if I just zoom in a little bit, let's zoom in right on that asymptote. So again, you can see our line, and here's the two pieces. So that asymptote is vertical, and here are my invariants, which you can see. Okay, so that's what we talked about last time, all those pieces. Now we're going to use all of those exact same ideas to deal with now a quadratic function, which I do have the equation for, which is nice. So let's do exactly what we did in the previous example. So let's go talk about the vertical asymptote here. Now, if I can take the original quadratic function, x minus 1 squared, and set that equal to 0, I should be able to find the value of x that makes this possible. Okay, essentially, I'm trying to locate the vertical asymptote here. Now, I've got to get x by itself. It's being squared. So if we square root both sides, that tells us that x minus 1 is equal to 0. So x should be equal to 1. Essentially, this is your 0. Okay, so my vertical asymptote, I know, now should go through that vertex. Okay. So there it is. Now we can even label it as x equals 1. Now, again, our horizontal asymptote, so that's vertical, our horizontal asymptote is going to be y equals 0. Again, the degree of the top is less than degree of the bottom. This time the degree on top is 0. On the bottom it's 2. Having that disparity gives us that y equals 0 for our horizontal asymptote. So we should include that as well. Okay. Now we got to go find our invariant points like we did before. So let's give us a different color then. Invariant points. Same thing is true for quadratic. So if that if the value of that original function is equal to 1 or -1, I should be able to find some invariant points. So let's set our original quadratic function equal to 1. We'll deal with this scenario first, and then we'll talk about the other case. Where it could be equal to -1. I might just run out of room, so if I just write it in here for now so I don't forget, I can move it around. So let's deal with the positive case first. Again, I need to square root both sides, so x minus 1 is going to be equal to 1, so x equals 2. That means one of my invariant points is 2, 1. Now let's talk about this case. Before I do that, actually, I did make one mistake here, and I just clued in. Let's move this down. When I actually take this square root, I do technically have two answers. what I did first wasn't incorrect, it just was a partial solution. So all I need to add here is the fact that this could either be a positive or a -1 when I take that square root. That means this gets split up into two cases. So on the one hand, if I use the +1 version, the principal root, and add 1 to both sides, this is going to give me x is equal to 2. The other scenario is x minus 1 is equal to -1. Okay, the other root. If I add 1 to both sides here, this will say that x is equal to 0, which makes my other point 0, 1. So I do have two invariant points coming out of that one case. Now I can go talk about this one. So underneath, if I try to square root both sides to get x by itself, we know we run into a problem. I cannot, in our real number system, take the square root of -1. I get a non-real answer. So this doesn't actually exist. There is no value of x here to satisfy this equation. I still do have two invariant points, but they only come from one of the cases. I'm not going to have a point where y is equal to -1. So let's go graph the other two that we have. So 2, 1 is one of them. You can see it right there. I'll keep it color-coded for us. So there's 2, 1. And then 0, 1 is my other invariant point. Okay, so I know I'm not going to have one down here at -1 because my two invariant points are here, and I can't cross that horizontal asymptote which we've drawn in. I can't cross that vertical asymptote which we've also drawn in. So now I've got a good idea of what my graph is actually going to look like. So we can go again, remembering that I'm going to get infinitely close to those asymptotes, but never actually crossing them. You can see your reciprocal graph being formed. Now this looks a bit different than our linear reciprocal, where I had two distinct parts on those opposite sides. The shape, I still have two distinct parts, but the shape is a little different. Okay, so here would be my reciprocal. Now we could look at some of the things we noticed here. So the main difference is I do have to remember that I have those two different cases for invariance, but I could potentially get 2 points from one of those cases. So we could say there are 2 invariant points that satisfy f of x is equal to 1, but none where f of x is equal to -1. Now this won't always be the case. Sometimes my +1 case might yield me no points, and my -1 case might actually give me the points. So it could change, so be very careful with your negatives here. And you even watched me make the same mistake, and I had to go back in because I forgot about that. So it does happen. So just take your time as you're learning this and go slow. So let's take a flip over, and we'll talk about some of the other types that we could have. So as a recall, the x-intercepts, or the zeros in a graph, those are going to become your vertical asymptotes, because when I take the reciprocal, I'm not going to be able to do it. It will give me an answer that doesn't exist. Okay, for this reason, we could have 3 situations with the reciprocal of a quadratic. So one shape, you might have no vertical asymptotes, which we'll see down below. We could have one vertical asymptote, like we saw in the previous one. So since I only had one factor here, technically 2, but that factor is the same, so I do have the same 0, you're going to see one vertical asymptote, and it will look and have this shape. Or I could have 2 distinct vertical asymptotes where I have 2 distinct factors or 2 distinct zeros. Okay, so we'll take a look at all of these cases. So as our first example, let's take this and try to sketch the graph. So we'll do what we did before and try to find some important points. You might hear them also be called critical points. Okay, so these are just important on the graph. Okay, they give us a bit of information to be able to draw it. So our f of x is going to be on the bottom. So f of x equals -2 x squared minus 0.5. Now, the form of this quadratic doesn't tell me a whole lot of information about it, so we're going to rearrange it into a little bit of a different form, vertex form, that gives me more information, or it could be called standard form as well. So -2 will factor out, so I'm going to have x squared minus, this would now say, I'm actually going to change that to a plus since I'm factoring out the negative sign, so this will be plus 1/4. I'm going to actually switch it to a fraction here also. Now, in this format, I could also say that -2 is essentially my a value. And what I mean by that is f of x equals ax. Actually, let's do ax minus p squared plus q. So this would be vertex form, where p and q would tell me the coordinates of the vertex. A would tell me that stretch amount, how much my graph is either getting pulled or flattened. Okay, so since it's a whole number and it's negative, I know it should open downwards. The whole number tells me that our values are getting twice as big. Instead of, if it would be a fraction, my values would have gotten squished by that amount. So let's kind of make this look like this form. So the number attached to x right now, there isn't one, so it's technically 0. So x minus 0 squared, we'll add a big bracket, and this is still plus 1/4. Okay. Now, since that value is 0, I can see that the x coordinate of my vertex is 0. Now, this 2 that's on the outside would technically have to apply to this constant as well, since it's in the brackets. So I should be able to write it as x minus 0 squared, and this would technically be minus 1/2 on the end if I actually distribute that 2 to both parts. Now I can see what my vertex is going to be. So my vertex is actually 0, -1/2. Okay, so that's an important point. Okay, we always talk about in quadratics the maximum or the minimum. So our vertex is that maximum or minimum. This time it is a maximum since my quadratic opens downwards. So this should be the highest point on there. Everything else falls downwards. Okay, so if I plot that point, we can graph it. So 0, -1/2, roughly here. And again, it doesn't have to be perfect. Let's make it a brighter color so it's easier to see. Let's make it red. Okay, so there's my vertex. Okay, so that was an important point to have. We can go then and talk about our vertical asymptotes then. So if I take this, we can try to solve for those vertical asymptotes. Now remember that if I'm trying to find that, I'm looking for the value that makes this 0. So I need to find x in order to make that 0. So let's talk about our vertical asymptote. If it's -2x squared minus 0.5, I want to make that 0. So let's add a half to both sides. So -2x squared equals 0.5. Divide both sides by -2 before I take care of that exponent. So x squared equals, that should be 4, I believe. No, I'm terribly wrong with that. So let's divide that by 2. That is negative, yeah. So -1/4. But now I run into an issue because I can't actually square root that negative. So if I can't actually find a value here, so therefore, no vertical asymptote. So I know I don't have a vertical asymptote here. So we can look at these 3 shapes, and the shape I'm really going to have is one that looks like this, the one with no vertical asymptote when I go to draw this. I do know that I have a horizontal asymptote for the same reasons as before. My degree on the top is less than my degree on the bottom. So I know I've got a horizontal asymptote. Okay, so that's great. And I know my vertex. I know there's no vertical one. So technically, I have enough information here to draw this. But let's go ahead and get our invariant points as well, just so we can be sure. Now, if I'm going to do these invariant points, just be very careful with the negative signs again. Okay, so let's say that -2x squared minus 0.5 is equal to 1, or it's equal to -1. Okay, now if it's equal to 1, let's do that side first. So negative 2x squared equals 1.5. Divide by negative 2, divide by negative 2 gives me x squared equals, so 1.5 divided by negative 2. Doesn't really matter what the number is because that's 3/4. Again, I can't square root a negative. So this one doesn't exist. So this case with the positive one does not give me any points that I can use. Now I've got to check this case. So let's add our half to both sides again. And that would give me, and again, I'm doing this for our sake, that I don't mess up adding, because it happens. There's my negative 0.5, and we'll divide that by negative 2, positive 0.25. That means when I square root it, I get 2 answers. X could either equal positive or negative 0.5. These are my 2 points. So that means, so therefore, it could be 0.5 comma negative 1, or it could be negative 0.5 comma negative 1. Those are going to be our 2 invariant points. Let's go plot them. So it could be, we said either positive or negative. Okay. Now, if I were to do this and graph it as it is, this graph, connecting these 3 points in this way, would give me the original quadratic equation. But we're not asked to graph that. I need the reciprocal quadratic equation. Now, this vertex is the vertex of the original. In order to get the vertex of the reciprocal, flip the y value over. So my reciprocal version of that vertex, this is going to translate into 0, negative 2. So this one would be on the graph y equals 1 over f of x. Since we're taking the reciprocal of y, the vertex I actually want, vertex, I say that loosely, so the vertex translated onto the reciprocal graph is actually down below. So we could say this is the original vertex. Okay, now I have enough information to graph my reciprocal. I know where my asymptote is. I've got my invariant points. I've got one other critical point. Now I should be able to graph this. And we'll check it in our calculator to make sure we've done everything correctly. But I find an easier way to graph this is to flip your paper, rotate it, and then draw it out. So you won't see it, but my iPad is upside down. Now, just remember that I cannot actually cross those asymptotes. So get infinitely close or as close as your paper and pen will allow you. But there's what my graph is going to look like. So if we go to graph this, I'll graph both on here, and we'll show you what they both look like. So the original was negative 2x squared minus 0.5, and then we'll bold the reciprocal. So get over to that left side, enter it, and we'll do 1 over, and we'll make sure we have some brackets. So negative 2x squared minus 0.5, close the bracket, graph. Now I'll have to change my graph back. Let's finish this thinking. So new standards, there we go. Okay, so now you can see the original on there as well as the reciprocal version. Now if I just zoom in a little bit, right on, yeah, let's zoom in right on the origin. We should see our peak or our minimum right about there. Okay, just like we predicted, okay? So there's our graph, it's perfect. We've got all the pieces, we've labeled some important critical points. We've got everything we need here. Okay, so let's try another one that might look a little different. Now, the previous one we did not have a vertical asymptote. Now this one, I can already tell you we'll have 2, because I've got 2 distinct factors here. So let's go find those vertical asymptotes first. So our vertical asymptotes will come from the factors. Okay, so that means one of them is 2, and my other factor is x plus 2 is 0, so x is equal to negative 2. So there's my 2 vertical asymptotes already, and I always remember I have to do a horizontal asymptote. Since my degree on top is less than the degree on the bottom, that will just leave us with the x-axis. So let's go label those right now so we don't forget. So x is 2, There's one of them. X is -2. There's the other. And axis. So now we've really split this quadrant or this coordinate plane up into a lot of different things. So we need to be very careful on where our points are to label everything. So we've got our asymptotes. This is good. Now, if we can find the vertex of the original, we can translate that into the critical point that we need for the reciprocal. So let's go find that. Vertex of f of x. Okay, so if it's x minus 2x plus 2, this factored form is a difference of squares. So when I actually go to translate it back, that's going to be x squared minus 4. Now I do want to locate its vertex, so we can try to put it into that vertex form of a quadratic we had before, which will look like x minus 0 squared, again, minus 4. I've got an a value in front, which is just 1, because that's the coefficient of my x squared. So therefore, my vertex is 0, -4, which means, let's do this purple maybe, vertex translated to reciprocal, that means that point becomes 0, -1/4. Okay, so this is the point that's actually on my reciprocal graph. So I'm going to plot that point roughly to give us an idea. So that's 0, -1/4. Yeah, somewhere here. And again, it doesn't have to be perfect, just a rough estimate of where that point should be. And we'll graph it again just to check. So I've got my point plotted. Now I do need some invariant points as well. I've got one point here. Now again, just by looking, I know I can't go up and I can't go out. So I know it has to follow that shape kind of downwards. That gives us a rough idea of where this should be. So let's go find our invariant points now. Invariant points. Okay, so we said that function was x squared minus 4. So that could either be equal to 1 or, remember, it could be -1. So we need to check both cases just to make sure we choose the right sign. So x squared minus 4 equals -1. So check the positive one first. X squared could be equal to 5. So that means x is equal to plus or minus √5. And it's difficult to kind of graph that. So we're going to just take the decimal estimate of it to give us a rough idea. So roughly 2.2. Positive or negative 2.2 approximately. They'll just give us enough information to graph it. Now let's check the other one. So x squared could be equal to, this time, that is going to be, what am I doing here? 3. So x is going to be equal to plus or minus √3, which again will take just the rough estimate of that decimal, about 1.7. Positive or negative 1.7, just enough to graph. Okay. Now graphing it isn't always perfect. Because of this, it is just an estimate, a sketch, which is totally fine. So when my y value is 1, I'm going to have an x at positive 2.2, so on this side of those asymptotes. So roughly here, and 1 on the other side, symmetrical. Okay, so 1 at positive 2, 1 at negative 2-ish. Now we've got to do the -1 cases. So I could be at positive 1.7. So 1.7 roughly here, but remember, we're at the -1 side of things, so down below. And again, same exact point replicated symmetrically near the other end. So there's my positive and negative 1.7s. They are both with their y value of that -1 for our invariance, and my 2.2s with their positive 1 y value. So now I have enough information. I have enough critical points to see the shape of this. Now, we'll work from left to right. So on this critical point, I can't cross the asymptotes. So just like before, I know I get close to them, but don't cross. Now in the middle, you can see that my line has to go through those 3 points as best you can. So again, don't cross those asymptotes, but get close. And lastly, there's my point for my last section. So there you go. There's the graph of your reciprocal this time. Again, you've got all your critical points, exactly the same how we solved them for the linear versions, just with the quadratic instead. Okay, so we'll do the next one as well. So if we start to find, do these in the same order every time, the practice gets a little easier. So we'll do vertical asymptote first. So our vertical asymptote of 3x minus 1 squared, that needs to be equal to 0, which means that x minus 1 squared is still equal to 0 when you divide 3 on both sides. Square root it, and you get x minus 1 equals 0, so x equals 1. There's our vertical asymptote, and again, our horizontal asymptote is y equals 0 once again. So label those lines so we know where our points are going to go. Now we can go find some invariant points. So just like before, points. So that means that 3x minus 1 squared equals to 1, or could be equal to negative 1. Okay, let's do the negative 1 case first this time. So if I divide by 3 on both sides, I'm going to get negative 1/3. Oops. Squared equals negative 1/3. Square root both sides, and you can't. So this side doesn't exist. So I know my invariant points have to come from the positive case. So x minus 1 squared equals 1/3. Square root both sides. And we're going to have to deal with some fractions here, which is okay. So square root of 1/3, and that's plus or minus. Add 1 to both sides, and we get 1 plus or minus the square root of 1/3. Now we're going to make that look a bit nicer. So x equals 1 plus or minus. If I take the square root of this, I get 1 over root 3. But we don't like to leave radicals on the bottom. So we'll rationalize it by multiplying top and bottom by root 3. This will change it so it will say root 3/3. So you could leave it like this, or you can combine these and say that it's going to be 3 plus or minus root 3/3. And again, we'll take the decimal equivalent to make it easier to graph. So if you plug those in your calculator and get both versions, you're going to see that x equals either 1.58 or 0.42. So there's your 2 invariant points. So we'll go graph them, and again, this will be roughly, because it's a decimal, so either 1.58, and this is positive 1, so up above, and 0.42, and again, 1, so up above. Okay, so I've got my 2 invariant points. We can go find the vertex of this original one also, just to see. So let's do it up here. Vertex of f of x. Now that function is 3x minus 1 squared. Now there's no constant on the end, so essentially that's like saying it's plus 0. So my vertex then is 1, 0. Now, if we try to do the vertex of the vertex translated onto the reciprocal graph, so let's translate to reciprocal. You're going to see that I actually can't flip this, because then it will tell me it's 1, 1/0. This doesn't exist. I can't actually have 1/0. So there is no other point to try. I can't translate this vertex to the other graph. So I have everything I need now. I have my two invariant points, and I can make my shape. So we'll go up to the asymptotes and down to the other one, and same shape on the opposite side. There you go. So there's your shape. So we can graph this also, just to check that we're still doing okay. So 3x minus 1, close the bracket, square it, and we'll flip this one. So 1 over, actually let's clear it out, it'll be easier. 1 over, and this is 3, another bracket, x minus 1, close it, square, close it, graph. Okay, so there would have been the original. And now you can see the two pieces that we've drawn, again, avoiding that asymptote. So there's your pieces. Okay, we didn't have the original graph on here, but if we did, it would go right through those invariant points. If you want to give it a quick sketch, your vertex would have been here, because that was our vertical asymptote. It opens upwards since the A is positive, so it'll go up this way through those invariant points. Rough graph, but it does get the point across that this is what it would look like and have that shape. Okay. So yes, it does work, and it works the same way in all of them. As long as we can find some aspects of the original, the important things. I spelled invariant wrong, or did I? No, I didn't. It just looks like the N is missing. As long as you find those critical points, the important things, plot them all, then visualize what the shape of that graph is going to look like. So you can actually go backwards. So we've always started with the graph or with the equation and drawn the graph. But we could go backwards and take the graph and translate it as well. So if I look at this one, you can see that there's one vertical asymptote, which means that I essentially only have one factor to deal with. So since that's x equals 3, the factor part is x minus 3, just by working backwards, because that would then be equal to 0, because I'm going to subtract 3 from both sides. Now, since there's only one of these, but it has this shape, it has to be quadratic, not linear, so that same factor has to show up twice. So I could start building my original function f of x, and that's going to be x minus 3 squared. Now, I just don't know if it's positive or negative, but what you can see is that this opens downwards. Okay, so my vertex of the original would have been right on the x-axis, right there, because this is the value that gives me that asymptote. Now, I don't see any points up above on the line y is equal to 1. That means there's no invariant points there. Okay, my only invariant points are on the bottom. Now, I don't know where they are exactly. I can't tell you the number because it's partway through, but there's 3 points right there that you can draw your original. And you can see the only way to connect those is if this opens downwards. So now you know that the a value here should be negative. And I'm talking about the a value because my original function should be some form of ax squared plus bx plus c, or it's ax minus p squared plus q. Okay, you can complete the square on this to get this one. Either way, a is the number in front of x squared, which has to be negative. Okay, so therefore, a is going to be negative. Okay, so we can say that y equals a over f of x, which is negative 1 over x minus 3 squared. So just by analyzing a couple points, you can build that equation as well. Now, I'm kind of guessing that it's negative 1 here because I haven't actually taken a point and plugged it in here to actually prove it's negative 1. Okay. You could do it provided you had enough information to get an exact point. Doesn't look like I have enough information to do that here, so we can assume that it is negative 1. Okay, usually if it's not, you'd have a way of finding an exact point to plug in for x and y, and you could solve for a to really nail it down. But here it's going to be negative 1. I just don't have a way of doing it. Let's talk about this one as well. So there isn't a vertical asymptote, which means that this isn't going to have one of those factors on the bottom. So it's going to be a little different in how we approach this one. So if I'm looking at this the way it is, there is no vertical asymptote, okay? So we're going to say, and we're going to take this piece by piece, and we're going to start building our original quadratic. Okay, so we're asked to graph the original function given the reciprocal. So this is what we want to graph. Now, these are all of the points that I know for certain. Now, these are on the reciprocal graph. That means I should have a way of getting the original ones by flipping the value. So that point that's 1 1/4, that would translate to 1 4. 2 comma 1. Notice that's a 1. This is going to be an invariant point. It's not going to change. So 2 comma 1. This one will change to 3 4. So all of these points in red would be on the original. That point right here would be an invariant point. Okay, so that's pretty important. And now that I know that, I've got a good idea that my graph is going to open upwards. Okay, and if it opens upwards, I'm going to have a minimum. So of these points, I already see my vertex because it's the one that's the lowest in between these two with the same y value. So I know that I've got my vertex. Okay, so that's the vertex right there. So if I have the vertex, that means that I could substitute in some points. X minus 2 squared plus 1. The 2 and the 1 represent the vertex. Pick another point for x and y, and you can solve for a. Let's pick 3, 4. So 4 goes in for y. A stays because I don't know it. 3 minus 2 squared plus 1. So you're going to end up with 4 is equal to a plus 1. So a is equal to 3. And therefore, your original function is y equals 3 x minus 2 squared plus 1. So there's your original. That's a terrible box. There's the original. You could graph it also. I kind of made a mess of this grid, but yeah, we can graph it as well. I'm going to use not red. Let's use pink. So it'll go up this way. Okay, it opens upwards. The vertex is that invariant point. I'm not really sure where it crosses the y-axis. I didn't actually solve for it, so I don't know the exact value, but this is what the shape is going to look like. Okay, there is one more that we can talk about. Now, it says consider the quadratic function f of x equals ax squared plus bx plus c. So that would be just the original one, but they're giving us the graph of the reciprocal. So there's just a couple pieces here. So if the y-intercept of g of x, now that's the one that's graphed here in blue, if the y-intercept is -1/3, state the y-intercept of the original. So we learned that all I need to do really is flip the value of this, take the reciprocal, and I've got the other version I need. So if this is -1/3, if I flip that over, my y-intercept of the original should be -3. And I can't even see it on my graph, so I'm just going to give us a dot right here, just because that's the best I can do without making a mess of things. So that y-intercept is going to be -3 somewhere here. So part B then says, given the minimum point of g of x is at 3, -1, so 3, -1, that's the minimum, sketch the graph of f of x on this grid. Now, they didn't really tell me a lot, but that number is really important, -1. This is an invariant point. It doesn't move. So that point will be on the other grid. Now, they've told me something very specific, but also very generic at the same time. They said the original function is quadratic. If this point doesn't move, and that's the y-intercept, there's only one quadratic graph that goes through those 2 points, and it opens downwards. I have the rough shape that I need to. Okay, so my graph roughly will look like something like this, a quadratic that opens downwards. And I'll graph it for you just to make sure. So I've got everything I need for the original. State the maximum point on the graph, y equals f of x. Now that's going to be our invariant point. Since this opens downwards, I do have a maximum. The maximum is the vertex, and the vertex is an invariant point. So my vertex is going to be 3, -1. The minimum of one of them becomes the maximum of the other. Express f of x in the form provided. So I need to put it in vertex form. I know what the vertex is. I have the intercept, so I have another point. I can solve for a. So let's go do that. Now, when I did this the first time, I made a mess of things because I forgot a negative. So be very, very careful. That f of x is going to be our y-intercept. So we're going to make it -3. That's going to be equal to a, which we're trying to locate. X is going to be the coordinate of that y-intercept. So that's going to be 0. Minus the x coordinate of our vertex, which is 3. Square it. Add the coordinate of the y coordinate of our vertex. And this is where I made my first mistake. I put +1, but it actually should be -1. You don't think it makes a big difference, but when you go to graph it, it doesn't look anything like you expect. So be very careful. So there's all the things in the right place. Now we just got to solve for a. So -3 is going to be equal to a. That'll be -3 in the brackets. Squared is 9. That's -1. So we're going to have -3 is equal to 9a minus 1. That means that if I add 1 to both, I get -2, and that's equal to 9a. So a is equal to -2/9. There's my number. Doesn't look great, but it is right. So therefore, f of x equals -2/9, x minus 3 squared, and this is going to be -1. So there is our function in the form we've been asked to provide. So there it is. Now we're asked to express it in just expanded general form. So let's multiply all these things together. So f of x equals -2/9 x squared minus 6x plus 9 minus 1. Now when you distribute everything in, collect all of your like terms, you get -2/9 x squared plus 4/3x minus 3. So I've skipped a couple of those steps because I'm confident you're able to do this, and this is what you should end up with on the end. Now, it's going to be pretty hard to put all of those things into this calculator, so I believe I've got them open here. So here is the same thing that we see. So let's turn this one off for now. So here's the original. Okay, so here's essentially what I've been asked to find the reciprocal of. Now, the reason why I was able to graph it is because I used my original formula, which was, I believe, here. So you can see this is where I did it wrong the first time. Let's get rid of that one. So here's the form I was asked for, that -2/9 x minus 3 squared minus 1. That's what I graphed in black. So when I do the reciprocal, I effectively just did 1 divided by it, and it gave me this one. Now we can see some of those critical points. My vertex, 3, -1, just like we stated. My y-intercept, 0, -3, again, just like we stated. And all of those critical points happen around that -1. That's where the invariant point is. You know, you don't see 1 or y is equal to +1, just like we don't in our graph also. So this does work. It works out very, very nicely. So there's your quadratic reciprocals. On the back, you do have just a little bit of a summary which talks about all the things that I just talked about. And you have one example that kind of walks you through it. So again, please make sure that you do ask those questions when you need them. And we will see you next time.